Picture two rocky worlds, born around the exact same star at roughly the exact same time. Today, one of them still seems to be clinging to a real atmosphere. The other shows no trace of one at all. That contrast didn't come from guesswork or a dramatic press release. It came from years of patient, layered observation, and it's turning into one of the most important side-by-side comparisons currently available in the hunt for livable worlds beyond our own. Here's the actual setup, and none of it needs exaggeration to be worth your time. If anything, the real version is more compelling than a fabricated one, because every piece of it can actually be traced back to a named researcher, a published paper, and a specific measurement someone else could go check for themselves. Roughly 48 light-years from Earth, in the constellation Cetus, sits a small, calm, roughly 3 billion-year-old red dwarf named LHS 1140, also known in catalogs as Gliese 3053. At least 3 planets orbit it, but 2 of them, LHS 1140b and LHS 1140c, sit close enough in size and location that scientists have essentially been able to study them as a matched pair, a rare setup where 2 rocky planets share a host star, an age, and a formation history, differing mainly in distance and exposure to radiation. First discovered back in 2017, the system has spent years quietly becoming one of the most closely studied laboratories in exoplanet science, precisely because opportunities like this, 2 comparable rocky worlds around one star, don't come along often. LHS 1140b is the headline planet of the pair. At about 1.73 Earth radii and roughly 5.6 Earth masses, it sits inside its star's habitable zone, the band of distance where surface temperatures could theoretically support liquid water. It also happens to be the second closest known temperate transiting planet to Earth, which makes it one of the rare rocky worlds close enough and large enough for current instruments to actually attempt real atmospheric characterization rather than just theorizing about it. LHS 1140c, meanwhile, orbits tighter and takes a stronger radiation hit from the star. Both planets sit right around what's called the radius valley, a size gap roughly between 1.5 and 2 Earth radii where planets show up far less often than statistics would predict. The leading explanation is that this gap marks a dividing line. Rocky super-Earths that lost any early atmosphere on one side, puffier sub-Neptune type worlds that managed to hold onto theirs on the other. Landing directly on that boundary is exactly why this system matters so much. These aren't planets settled comfortably on one side of that line. They're planets that may still be in the process of ending up there. James Webb entered the story first in a 2024 study led by Charles Cadieux at the University of Montreal using the NIRIS instrument to observe LHS 1140b through transmission spectroscopy, reading the chemical fingerprint left in starlight as it filters through a planet's atmosphere during a transit. Because LHS 1140b's measured density came out lower than a purely rocky world should have, researchers were trying to settle a real question. Was this a mini Neptune with a thin leftover hydrogen shell, or an actual water world? Potentially, holding somewhere between 9 and 19% of its mass in water? Distinguishing between those two scenarios needed exactly the kind of detailed atmospheric spectrum only a space telescope like Webb could deliver. During that observing run, the team got an unplanned bonus. LHS 1140c happened to transit the star at the same time, handing researchers a rare simultaneous look at both planets using identical instrumentation under identical conditions, a coincidence of timing nobody had specifically scheduled for. That first Webb dataset, though, came back tangled. The combined spectrum showed a clear signature of stellar contamination, specifically unocculted faculae, bright magnetically active patches on the star's surface not directly covered by the transiting planet, estimated to cover roughly 20% of the visible stellar disk. That kind of contamination can distort or completely bury a genuine atmospheric signal, so while the observation was valuable, it didn't cleanly answer whether LHS 1140b actually had an atmosphere. The real breakthrough came 2 years later, in 2026, and it's important to be accurate about where it came from, because it wasn't Webb. A follow-up effort, again involving Charles Cadieux alongside Shreyas Visapragada at Carnegie Science Observatories, switched to a completely different instrument. The ground-based Magellan Clay Telescope in Chile, using a spectrograph called Winnared Purpose, built to slice incoming light into extremely fine wavelength detail across the near-infrared. The Clay Telescope's mirror is 6.5 meters wide, matching Webb's own segmented mirror almost exactly. But the deciding factor here wasn't size. It was Winnared's specific sensitivity to a narrow signature, helium physically escaping a planet's upper atmosphere, a signal precise enough that catching it cleanly genuinely requires this specific kind of high-resolution ground-based instrument rather than raw aperture alone. That signature carries real theoretical weight. During his PhD research, Coway Cherubim built a model showing that lighter gases like hydrogen should bleed off a small, heavily irradiated planet faster than heavier helium does, meaning any atmosphere still clinging. To a world like LHS 1140b, after billions of years of radiation exposure, should skew increasingly helium-rich over time as the lighter gas escapes first. If accurate, detecting escaping helium wouldn't just be interesting. It would be the direct fingerprint of an atmosphere that's genuinely still there, slowly thinning rather than already gone, the chemical residue of everything lighter that's already boiled away over billions of years. Observing LHS 1140b during a September 2024 transit, the team found precisely that: helium leaking from the upper atmosphere, driven outward by the star's X-ray and extreme ultraviolet output. Published in Science on July 17, 2026, the result stands as the first confirmed atmosphere ever detected on any rocky exoplanet inside a habitable zone, a genuine first in a search that, until now, had only ever turned up candidates, never a confirmed survivor. The part that turns this into a two-planet story, rather than a single win, is what happened when the same technique was pointed at LHS 1140EC. Nothing. No helium signature at all. And there's a second twist. Revisiting earlier data from 2025, the team found that the helium signal at LHS 1140b itself had vanished by that point, present in the September 2024 transit, gone a year later. That's not an error. It's evidence the planet's rate of atmospheric loss isn't constant. It fluctuates, most likely. Tracking the star's own activity cycle, its high-energy output rising and falling much the way our sun's does across roughly 11 years. Scientists now interpret this as an upper atmosphere skewed toward helium and thinned of hydrogen, with heavier gases potentially still locked in at lower altitudes, exactly the layered structure Cherubim's model predicted for a world losing its lightest gas first, while quietly holding on to the rest. It's a genuinely elegant piece of detective work. A single missing signal, absent one year and present the next, becoming the thread that reveals an entire ongoing process rather than a one-time event. So here's the actual comparison sitting at the center of this story. Two similarly sized rocky planets circling the same aging star at slightly different distances, exposed to noticeably different radiation levels. One, LHS 1140b, shows genuine, if inconsistent, evidence of an atmosphere still fighting to hang on, fractionating rather than vanishing outright. The other, LHS 1140c, closer in and harder, hit by radiation, shows nothing at all, at least not yet, under identical detection methods. Robin Wordsworth, one of the scientists helping interpret these findings, has pointed out why this specific technique matters well, beyond this one star system. Because helium detection works from the ground, it doesn't compete for the scarce, heavily oversubscribed observing time Webb requires. Cherubim's model can now screen, advance, flagging which ones are statistically likely to show a detectable helium outflow. Those that pass become genuine priority targets for the far more expensive, far more limited Webb observations needed to search for water, carbon dioxide, or anything else that would matter more directly for actual habitability. That's the real significance buried under the headline. It's not simply that helium leaked off one planet and not the other. It's that researchers now have a working, testable filter for deciding which rocky worlds deserve the enormous cost of deeper study, paired with a live, ongoing example of what a planet caught mid-transformation, still partially atmosphere intact, still losing pieces of itself to space, genuinely looks like once you can measure it, rather than just model it. It's worth being clear about the limits here too. Detecting helium escape doesn't confirm LHS 1140b is habitable, and it's nowhere close to finding water, oxygen, or any actual sign of biology. What it confirms is narrower and arguably more foundational. A rocky planet sitting inside a habitable zone can hold onto some form of atmosphere despite billions of years of stellar radiation, something never directly confirmed for any such world before this. Every previous rocky habitable zone candidate studied this closely had come back either bare or hopelessly ambiguous. This is the first clean exception. And LHS 1140C's silence isn't necessarily the final word either. It could mean the planet genuinely lost its atmosphere outright under stronger radiation. It could mean whatever's left there is structured in a way this particular method simply can't catch yet. Researchers have already flagged it for continued observation from the ground and eventually from Webb again, rather than treating today's non-detection as closed. Step back. And this is what an honest two-planet transformation story looks like, when it's built from real, peer-reviewed data, instead of manufactured drama. No signals, no aliens, just two rocky siblings orbiting the same star, sitting on opposite sides of the line that decides whether a planet keeps its air or loses it to space, one showing real, if unstable signs of survival, the other showing nothing yet at all. It took a Webb dataset to first flag the system as worth the attention, and a purpose-built, ground-based instrument years later to finally catch the difference between the two. It's worth appreciating the actual timeline behind all of this, because it says something honest about how this kind of science really works. The system was first discovered in 2017. Webb's detailed look came in 2024, and even that came back tangled by stellar contamination rather than delivering a clean answer. The helium detection that finally settled part of the question didn't arrive until July 2026, and even then, it depended on a specific theoretical model, a purpose-built instrument, and repeat observations across 2 separate years just to catch the signal changing shape over time. That's not a story that fits neatly into a single dramatic reveal. It's a story built slowly, one paper at a time, by researchers willing to keep looking even when the first attempt came back ambiguous. If you want to know what Webb finds the next time it looks directly at LHS 1140c, subscribe and turn on notifications, because this is exactly the kind of real, still developing story worth following as more data comes in.